Okay, this is the video for the Chemistry 1 practice test. I'm hoping I can get all of this onto one video. We'll have to see. But these problems will be pretty much exactly what you're going to see on the test that will be coming up next week. So, really, everything we've done this year in chemistry comes down to this point. This is where we get to use everything that we've learned so far. So in this particular case, I'm going to need to know equations, we learned about them, compounds, molar masses, periodic table, everything's coming together at once. So the first part of this problem, hydrogen gas is produced by dropping magnesium metal into hydrochloric acid according to the following reaction. Now this is a balanced equation. I promised you I would give you balanced equations in this particular case. What I do in any stoichiometry problem, I write down what I know. I write down what I'm given. So in this particular case, I know I have 6 grams of hydrogen chloride. Now when hydrogen chloride dissolves in water, it becomes hydrochloric acid. It's the same compound, it's just whether it's a gas, which it would be without water, or it's a substance dissolved in water. In that case, it's an ionic compound. Hydrogen chloride breaks apart to hydrogen ion and chloride ion. If you remember, this is a single replacement reaction. I have magnesium, an element, going in. I have another element, hydrogen, coming out. Hydrogen becomes an ion, hydrogen H+ and Cl-. Hydrogen becomes an ion when it dissolves in water. Therefore, the more active element is going to replace the less active element. The more active element is going to become an ion. In this case, magnesium is going to assume a +2 charge. Hydrogen is going to go from a +1 to a 0. And since I have 2 hydrogens, each hydrogen is going to receive 1 electron from magnesium, and that's the redox component of this, the oxidation reduction. So just so we can see, magnesium in this case is oxidized and hydrogen is reduced. And that's all based on the activity series, which we've learned about previously on this table sheet that we have. Now, I have 6 grams of hydrogen. I have 5 grams of magnesium. Now, those are my 2 reactants, as I can see. One of those reactants is going to run out over the course of this reaction. So the question is, which of these is going to run out first? Once this runs out, you're not going to be making any more product. So one of these is going to run out first. It's going to make less product, and therefore that particular substance is going to be the limiting reactant. Once that happens, you can't make any more product. So let's take a look. It's saying 6 grams of HCl reacts with 5 grams of magnesium. What is the limiting reactant? And how many liters of hydrogen gas at STP should be produced? And we're required to show all of our work because that's how I can tell you're actually doing the problem. So, first step is write down what I know. Then, changing grams to moles. Now hydrogen is approximately 1. Chlorine is approximately 35.5. So the gram molar mass would be 36.5 grams. That way my grams are going to cancel out. And if I can find my calculator, which I'm not sure where I put it. Alright, no luck finding my calculator, but I will need it for upcoming problems. You'll have to bear with me a moment. The problem is if I stop my video, then it's going to take a lot longer for me to upload because I have to edit it. So my apologies. But now I have my calculator. So 6.00 divided by 36.5. Again, I'm getting my grams canceled out by dividing. I'm left with moles. So I end up with, let's try that one more time, 6 divided by 36.5 is 0.164 moles approximately of hydrogen chloride. I'll do the same thing with magnesium. I got that 24.3 grams right here from the periodic table. So that becomes 5. My grams cancel out again. 5 divided by 24.3. So it's about 0.2. We'll call that 0.206 moles of magnesium. Now, that is how many moles. My equation is based on moles. That is why I need to change everything into moles. Moles tells me that I have 1 mole of magnesium will react with 2 moles of hydrogen chloride. I'll make 1 mole of magnesium chloride. I'll make 1 mole of hydrogen gas. That's my mole ratio. With that ratio, I can now tell however much of reactant I'll need or however much of product I'll need. Now in this particular case, it works in my best interest to calculate the amount of hydrogen because I'm going to have to do that later on anyway. How many liters of hydrogen gas at STP should be produced? So I'm going to, first with HCl, I'm going to find out how much hydrogen I make. What's my mole ratio? It's 1 mole of hydrogen, which I get from my mole ratio at the top, to 2 moles. 2 moles of hydrochloric acid. So my moles of hydrochloric acid cancel out. That's how I know I'm doing the right thing. And what I end up making here is about 0.082 moles of hydrogen gas. Again, because I basically took my number of moles of hydrochloric acid and divided it by 2 through my mole ratio. That's what I had to do. That's how much hydrogen gas. Because if I have 1 mole of HCl, I'd make half a mole of hydrogen gas. It's exactly the same thing. 2 moles of this, 1 mole of this, 4 moles of this, 2 moles of this, 6 moles of this, 3 moles of this. I'm always going to make half as much hydrogen gas in moles that I do with hydrogen chloride. Now for magnesium, I go, same idea. What's my ratio? I make for 1 mole of hydrogen, I use, I don't like these pencils, 1 mole of magnesium. I got that from my mole ratio. For every mole of magnesium that goes in, a mole of hydrogen gas comes out. So my moles of magnesium cancel out and I get 0.206 moles of hydrogen. What is this telling me? If all of my hydrochloric acid were used up, I would get 0.082 moles of hydrogen gas. If all of my moles of magnesium were used up, and I had enough hydrochloric acid to do it, I would make 2.206 moles of hydrogen. But the problem is, if all of this magnesium were to react, if I look at the ratio, for every 1 mole of this, I need 2 moles of this. For 0.2 moles of magnesium, I would need 0.4 moles of hydrochloric acid, which I do not have. So my hydrochloric acid is going to run out first. Once my hydrochloric acid is used up, I can only make this many moles of hydrogen gas. So that is my number to tell me how much product I'll make. Because the other question, this HCl is my limiting reactant. And now I'm only going to make that much hydrogen, because once this amount of hydrogen is made, my HCl is used up, I can't make any more hydrogen gas. So what do I do now? I have my moles of hydrogen. If you remember the steps for stoichiometry, it was balanced equation, units to moles, my mole ratio, then I get a certain mole value. In this case, I'm looking at a product, and then I go moles to units. So, in this particular case, it's asking for liters of hydrogen gas. 0.082 moles of hydrogen. I want to convert this. It's a gas at STP. All gases at STP are 22.4 liters over 1 mole. That way my moles cancel out, and I end up with 0.082 times 22.4, 1.8, we'll call that 1.84 liters of hydrogen. If I have this and I write down my units and I know what I have, I go back in my answer and I see, is that what I was supposed to get? And I see the answer is yes, that's what I was supposed to be looking for. So that problem is completed. That would be your answer. It can always help to circle your answer so that I know on your test what you're actually talking about. Now, this next one, if I can move it up a little bit more. Okay, I think that will all fit on the screen, but let me move it down and over a slight bit to be positive. A little crooked now. Again, I apologize for having low-tech solutions here. Alright, looks like it's focused. So, next question. Again, by now, we have to know iron 3 refers to the charge on each iron atom. This is a formula unit of iron 3 oxide. This is a molecule of carbon dioxide. This is a formula unit because it's a metal and a nonmetal. Metals and nonmetals exist as ions. The lowest ratio of ions is 2 iron 3 ions to 3 oxide ions. This is a molecule, 2 nonmetals. So this is a molecule. This actually exists in nature. This is carbon monoxide opposed to carbon dioxide. And I just realized here we have a typo. It should be 3 carbon monoxides. That's not actually relevant to the equation we're talking about, but it should be 3 carbon monoxides to 2 irons to 3 carbon dioxides. Is this a balanced equation now? 2 iron atoms, 2 iron atoms. 3 carbon atoms, 3 carbon atoms. 3 plus 3 is 6 oxygen atoms, 6 oxygen atoms. Unbalanced. Okay. Now, this question is asking iron 3 oxide. And again, the charge on each iron atom in this formula unit is plus 3. The oxygens are minus 2. Minus 2 plus 3, the best way, easiest way to balance them, I have 3 minus 2's and have 2 plus 3's. Never, never, never expect iron 3 to have a 3 as the number of atoms, because the 3 refers to the charge on the atom, not the number of atoms. We can't keep making that mistake. So, 84.8 grams of iron 3 oxide react with an excess of carbon monoxide. What does the excess mean? It means I have more than enough. I'm not going to run out of carbon monoxide. I don't even have to worry about how much carbon monoxide I have, because I'll always have enough to complete this reaction. How many grams of iron should be produced? So, first thing, write down what you know. 84.8 grams of iron 3 oxide. That I know. Then I need to find the gram molar mass for iron 3 oxide. So there's 2 atoms of iron. Damn pen. So I have 2 atoms of iron in my formula unit of iron 3 oxide. So that's 55.8 times 2. And then I have 3 oxygen atoms. Now 16 times 3, I do it in my head, that's 48. 159.6 is my gram molar mass for iron 3 oxide. And again, always balanced equation and then units to moles. So this would be 1 mole over 159.6 grams. Do the math here. It's 84.8 divided by 159.6. So that's 0.531, we'll call, because we're using 3 digits here. 0.531 moles of iron 3 oxide. Now, I don't have to calculate which is the limiting reactant here. I have this quantity that's going to run out because I have an excess of carbon monoxide. Now, if I looked at my mole ratio, for 1 mole of this, I need 3 moles of this. For approximately 0.5 moles of iron 3 oxide, I would need 1.5 moles of carbon, for 0.5 moles of iron 3 oxide, I would need 3 times that amount of carbon monoxide. So that means I'm dealing with 1.5 approximately moles of carbon monoxide that I would need for this problem. But I don't have to worry about it because it's an excess. Excess means I have more than I could ever possibly need of carbon monoxide. This is going to run out first. So stoichiometry, balanced equation, units to moles. Then we have a mole ratio here. 1 iron 3 oxide to 3 carbon monoxide, 2 irons, and 3 carbon dioxide. So I take this many moles of iron 3 oxide. With my mole ratio, I can figure out how much iron I will make. Now, I've set this up 2 different ways. I've set this up by saying 1 mole of iron 3 oxide over 2 moles of iron would equal, and this is my cross multiplication, 0.531 moles of iron 3 oxide over X. When I solve for X, my units of iron 3 oxide are going to cancel out. I'm left with moles of iron. If I do it this way, I get X equals 2 times 0.531 moles, which would equal 1.062, we'll round that off to 1.06 moles of iron. That was my cross multiplication I showed you when we first did this because I wanted you to break it into different steps. However, we have a simpler way. I have 0.531 moles of iron 3 oxide. This is one way of doing it. This is another way of doing it. Don't think you need to do both of these things. Watch what I do though. 0.531 moles of iron 3 oxide. I want to cancel that out. So I put that on the bottom. Where did I get 1 mole from? I got it right here from my balanced reaction. Now what do I care about? I want to find iron. My moles of iron 3 oxide cancel out. Same thing's going to happen here. 0.531 times 2 is 1.06 moles of iron that I end up making. Either way works just as well. I think this way is a little bit shorter, but if you're really a process person who needs to break it down into steps, that might be the way to go. Excuse me. Anyway, either one brings us to the same answer. Now, the question is how many grams of iron should be produced? Balanced equation, units to moles, mole ratio, cross multiply or cancel out. Last step is moles back to units. So 1.06 moles of iron times, and if I remember my gram molar mass of iron from the previous portion of this problem, it's 55.8 grams. I put that on the top so that I can cancel out moles on the bottom, and I end up getting 55.8 times 1.06 is, we'll call it 59.1. That all depends on where you're rounding. If you got a 59.3 or a 59.2, or 59.0. That's all based on where you round it off. As long as you're in the ballpark of what you should have gotten, we're fine. So 59.1 grams of iron is what I end up having. Now, the bottom thing says is if 55 grams of iron are produced in the above reaction, what is percent yield? So, percent yield is how much you actually get. We call that the actual yield. Over what was a theoretical yield. I did not perform this reaction. I just determined how much I should get based on the math. This is how much product I should get. This is how much iron we should get. I will point out this is an extremely important reaction. This is one of the ways that we make iron. Our society is still very much dependent on iron in order to make steel. And if you know the history of the world, most of the history of the world was based on who had iron and who didn't. And who was able to make iron easily conquered those who didn't have iron. I said Egypt was a long, well-established, very advanced civilization. But what happened? They had bronze. Other groups, like the Assyrians, had iron. The Assyrians were therefore able to conquer the Egyptians. This is the whole history of the world. That's why we have an iron age. That's why this is significant and relevant to really any subject you might want to study. What are the skeletons of our buildings that we build today made of? They're still made of mostly steel. Iron happens to be very abundant. Iron and carbon make steel. We still have a lot of steel making that goes on in this world today because steel is strong, iron is common, carbon is common, so we make lots of things out of steel. This would be my yield if I did my calculation. That's how much I should get. That's assuming a perfect world. That's assuming that every formula unit of iron 3 oxide can find every single molecule of carbon monoxide and proceed with the reaction. However, you have to understand, as this reaction proceeds, it's going to be much harder for each formula unit to find each mole of carbon monoxide because I'm getting more and more of this over time. So in a perfect world, every formula unit, every molecule would find each other. In the actual world, that doesn't happen. In this particular case, instead of making 59.1 grams, I made 55.0 grams. But that's my actual. My theoretical is what I should have made. Okay. Now this is percent yield, which should be a percent number. It's my actual, what I'm given. I would have to give this to you, or you'd have to see it over the course of a lab. And theoretical yield times 100. So if I actually plug in real numbers here, it'd be my actual yield, what I tell you you made, or in a lab, what you actually did make, over my calculated theoretical yield, and then multiply that by 100, and I get my percent yield, which in this case is 59.1 divided by, 55.0 divided by 59.1, which equals 0.930, so we'll call that times 100. My percent yield is about 93%. 93.1% if I want to be very specific. Okay. This is page 1. I think for processing time on my videos, I think I'm going to upload each page as we proceed. That way the video is going to be, each video is going to be a little bit shorter. So this will be the CHEM1 practice test page 1. I'll get to page 2, but I'm going to stop this video and upload that video first. So see you soon.